Hello, my name is Christian Conrad and I'm presenting a work on frequent elements with witnesses in data streams. In the traditional frequent elements problem in data streams, we're given a universe of size n. In this example, we have a universe of different colors and we have a stream of length m. An algorithm sees these items one by one. So for example, first it sees a green item, then a blue item, another green item. And once the algorithm has processed all the items in the stream, it has to output an element from the universe. Here, the blue item would be a good item because it occurs most of the time in the input stream. So the output can be either the most frequent item or maybe an item that appears at least d times for some integer d. Now, this problem has many applications. So for example, we can think of a network router, and suppose the network router needs to output the most frequent target IP address that it has seen in a specific time span. For example, if we think about a database log file, we might be interested in what is the most frequently updated or queried entry in a database log. But we can also, for example, think about social network graphs. Suppose we see the sequence of friendship updates in the social network graphs, then we could detect a node of large degree, which could, for example, be an influencer. Now, in this paper, we introduce a variant of the frequent elements problem, and we call it the frequent elements with witnesses problem in data streams. So the setup is identical to the frequent elements problem. We have a universe of size m, a stream of length m, but the difference that we see here is that I have annotated the items with the position in the stream where they appear. Now the algorithm processes these items again one by one, and once it has processed all these items, the output again needs to be a frequent element from the universe, so blue would still be a good output. However, it now needs to also produce a witness. And so what is a witness here? So this witness is a witness set that contains the positions of when a blue item appeared in the stream. So for example, we see that the blue item appeared at position 2, 5, 10, 12, 15, etc. We also see that some of the witnesses are missing. So for example, item number 11 is not part of this witness set, but we will see in the problem formulation on the next page that of course we would ideally want the witness set to be as complete as possible. Now, we can also think about witnesses slightly differently. So for example, if these items in the stream arrived with some metadata, then instead of outputting the timestamps of when this item appeared in the stream, we might as well output the metadata that arrived with the items. Now, in our applications, let's think about the network router example again. So we can output a frequent target IP address, but for example, the metadata could be the source IP addresses that come with this specific target IP address. So we would even know where these requests originate from. If we have a database log, we can, for example, output again the most frequently updated or queried entry. But if the log file also contains information about which user updated or queried these entries, then we could output these users as well. Similarly, with friendship updates, we can not only detect a node of large degree, but also their friends, so their neighbors in the social network graph. Okay, so this brings me to the problem formulation, the more precise problem formulation that we study. So we define the frequent elements with witnesses problem as follows. So we model the problem with a bipartite graph. The A vertices correspond to the universe of elements. So in the previous example, this would be the colors. And the B vertices would correspond to the metadata or the timestamps. And we assume for simplicity that the size of B is polynomial in n. We are also given an integer d, which will be upper bounded by the frequency of the most frequent item, so which corresponds in this graph to the maximum degree of an A node. The output then should be any A vertex together with at least d over alpha of its neighbors for some approximation factor alpha, meaning that ideally we would like to produce at least a witness set of size d. However, we allow for some approximation, and this is where alpha comes in. So the witness set doesn't necessarily have to be quite as large as d. So as an example, here we see, for example, the timestamps. If we have on the A side, we have our universe, then this would mean that the item arriving at time step 1 would be this one, the item arriving at time step 2 would be this one, this item arrives again at time step 3. So we can model the timestamp example here with a graph. But it allows for other examples as well. So here in a social network graph, for example, we could duplicate the universe or the users of the social network graphs. We can assign them as A vertices and B vertices. Now, whenever an edge in the social network graph between two users arrives, so for example between Alice and Bob, then we insert both Alice and Bob and Bob Alice into this graph. Then we see, for example, that we have a node DOM here, and this node DOM is connected to 4 other nodes. So DOM has 4 neighbors here, and this would be that the maximum degree here of an A vertex would be 4. So we can indeed ask this question for any d that's at most 4. And if we ask this question for d equals 4 and alpha equals 2, this would mean we have to produce an A node that has at least 2, so 4 divided by 2 neighbors. So for example, the valid output would be DOM together with the neighbors Alice and Charlie. But there are other solutions as well, so we might report Bob also with neighbors, with witnesses Alice and DOM. Okay. Now, we study this problem in 2 types of streaming models. The first model is the so-called insertion-only stream model. Here we simply see a sequence of the edges of the input graph in arbitrary order. We also study this problem in insertion-deletion streams, where the input is a sequence of edge insertions and deletions, also in arbitrary order. So for these 2 sequences here, they describe exactly the same graph. The only difference is that edges, here we introduce some additional edges in this sequence, so A1, B1 is introduced here, but then A1, B1 is deleted again. Okay, now our results are as follows. We basically resolve the space complexity of streaming algorithms for this problem up to polylogarithmic factors for a wide range of parameters. So insertion-only streams, if we would like to have an integral approximation factor alpha, which is polylogarithmic in n at most, then we give an algorithm with space O tilde of n plus n to the 1 over alpha times d, and O tilde hides polylogarithmic factors. We also give a lower bound that matches this upper bound up to polylogarithmic factors. So in fact, the lower bound is more precisely is this expression. So we divide both terms n and n to the 1 over alpha d by alpha square. But for polylogarithmic approximation factors, this sort of disappears in the omega tilde notation here. Okay, so in insertion-deletion streams for approximation factors up to root n, we have an algorithm with space d times n divided by alpha square, and we also match this space requirements up to polylogarithmic factors with a lower bound. This shows that the problem is much harder in insertion-deletion streams. Okay, now the main techniques for achieving these results on the algorithmic side is sampling, subsampling. There's a combination of reservoir sampling and degree counts, and we also use L0 sampling for insertion-deletion streams. And for lower bounds, we use communication complexity. More precisely, for insertion-only streams, we use multi-party, one-way multi-party communication game, and for insertion-deletion streams, we model this with a 2-party communication game. Now, I will very briefly talk a little bit about the insertion-only stream algorithm to give you an idea about the techniques that are being used. So our goal is to find an A node together with d over alpha of its neighbors. So now the challenge, of course, is that in the beginning of the stream, it's unclear which items will appear frequently later on. So we cannot simply collect witnesses arbitrarily, and because we would run out of space. Now, here's a special case. We look at a 2 approximation for this problem with space n plus d times root n. So then we run in parallel the following 2 strategies. So first strategy, we sample roughly root n A nodes, and we simply collect up to d half witnesses for each of these nodes. Now, when would this strategy succeed? Well, it would succeed if there are enough nodes of degree at least d half. So if there are omega of root n nodes of degree at least d half, then necessarily we would, or with high probability, we would sample one of these nodes and we're done. If this strategy doesn't work, then the following strategy would work. We count the degrees of all A vertices. Then we ignore the first d half witnesses of each A vertex. And only then we would start collecting witnesses. Now we know that the input stream contains at least one A vertex of degree d. So this A vertex would necessarily be picked up by this algorithm, and we would find a witness set of size d half. However, we need to make sure that we stay within the claimed space bound. And we saw that strategy 1 succeeds if there are at least omega of root n nodes of degree at least d half. Now let's suppose that there are fewer than root n nodes, or only O of root n nodes of degree at least d half. well, in that case, we would indeed stay within the space bound, because again, there are root and nodes of degree at least d12. Those witnesses would be collected, so we would collect up to d12 witnesses for these nodes, and would therefore require space d times root n. Now, we extend this strategy to arbitrary approximation factors, and the way we do it is, so we see that here we use these degree intervals from 0 up to d12, and this strategy uses the degree interval from d12 to d essentially to collect these witnesses. We need multiple degree intervals then when we have arbitrary approximation factors. And also we need to do something slightly more clever in step 2, which can be done using reservoir sampling and again counting these degrees. Okay, now as an outlook, I would like to discuss the following question. So the bound in insertion-only streams is n plus n to the 1 over alpha times d. So it goes down with as alpha increases. But the question really is this in fact sublinear space? Well, the input stream is of length m, which can be much longer than n. So yes, most likely this is sublinear space. But what the algorithm does, it counts degrees of all items that appear in the stream. And the question is really, do we really have to do that? Because for every item in the universe, or in the, we essentially have to keep a counter. So, so can this be avoided? And the answer is, of course, no, because we have a lower bound that matches this bound. However, what can we do to avoid that our algorithms actually need to count all these degrees or have a linear dependency on n in the space requirements? And we can introduce the following assumption. Suppose that there is an item in the input stream that appears at least epsilon m times for some epsilon larger to 0. So there is an item in the input stream that appears really very often. And indeed, then it appears that we can obtain algorithms that have space requirements quite a bit better than linear in n. And as a note, this assumption is, for example, also needed for the traditional frequent elements problem. So even without computing witnesses, if we have no assumption that an item appears relatively often in the stream, then we cannot really obtain sublinear space algorithms. Thank you very much.